Hi students, today we will study about the interference of light waves, Young's double slit experiment. In the previous experiment on geometric optics, we used the concept of light rays to examine what happens when light passes through a lens or reflects from a mirror. The next experiments are concerned with the subject of wave optics, which deals with the phenomena of interference, diffraction, and polarization of light. These phenomena cannot be sufficiently explained with ray optics, but we shall describe how the wave theory of light leads to a satisfying description of such phenomena. We need quantum mechanics. Our objectives are to explore the intensity distribution in the interference pattern and determine the wavelength of a diode laser. The phenomenon of interference in light wave from two sources was first demonstrated by Thomas Young in 1801. This was a crucial experiment because it added significantly to the evidence for the wave nature of light. For interference between two sources to be observed, these conditions must be met. First, the source must be coherent. They must maintain a constant phase with respect to each other. The waves must also have identical wavelengths, monochromatic light source. It is much easier to perform interference experiments with a laser beam than with an ordinary light source because the characteristics of laser beam are coherent, monochromatic, and collimated. Light from the laser beam arrives at a barrier that contains two parallel slits S1 and S2. The light diffracts through the slits and interferes in the space beyond the slits. A succession of Huygens wavelets then emerges from each slit. These two slits serve as a pair of coherent light sources because waves emerging from them originate from the same wavefront and therefore maintain a constant phase relationship. The light from the two slits produces a visible pattern on the screen. The pattern consists of a series of alternating bright and dark parallel bands called fringes. In diagram A, the two waves which leave the two slits in phase strike the screen at the central point P. As a result, a bright fringe is observed. In diagram B, the two waves also start in phase, but in this case, the upper wave has to travel one wavelength farther than the lower wave to reach point Q. A second bright fringe appears at this location. In diagram C, between points P and Q, the upper wave has fallen half a wavelength behind the lower wave. For this reason, a dark fringe is observed. The viewing screen is located a perpendicular distance L from the barrier containing two slits S1 and S2. These slits are separated by a distance D. To reach any arbitrary point P in the upper half of the screen, a wave from the lower slit must travel farther than a wave from the upper slit by a distance d sine theta. This distance is called the path difference delta. If we assume that R1 and R2 are parallel, which is approximately true if L is much greater than D, then delta gives by delta equals R2 minus R1 equals D sine theta. If delta is either 0 or some integer multiple of the wavelength, then the two waves are in phase at point P and constructive interference results. D sine theta equals m lambda. When delta is an odd multiple of lambda over 2, the two waves arriving at point P are 180 degrees out of phase and give rise to destructive interference. D sine theta equals m plus half lambda. Thus, the pattern on the screen is a succession of bright and dark bands. Let ym be the distance of the center of the mth bright band from the center of the central band. In addition to our assumption that L is much greater than D, we assume D is much greater than lambda. Under these conditions, theta is small. Thus, we can use the small angle approximation tan theta is approximately equal to sine theta. Then from the triangle OPQ in the figure below, we see that y bright equals lambda L over dm. Now, I want to focus on the intensity distribution in the interference pattern. The two waves arriving at point P have the same angular frequency omega and a constant phase difference phi. Assuming that the two waves have the same amplitude E naught, we can write the electric field intensities at P due to each wave as E1 equals E naught sine omega t and E2 equals E naught sine omega t plus phi. After some mathematical calculations, and since the intensity of a wave is proportional to the square of the electric field intensity, we reach the last equation shown on the screen. The graph shown on the screen is extremely important as it shows that the interference pattern consists of equally spaced bands, fringes, of equal intensity. As the number of slits increases as shown in the figure below, then primary maxima increase in intensity and become narrower. Secondary maxima decrease in intensity with respect to the primary maxima. Number of secondary maxima also increases, which is always n minus 2, where n is the number of slits. Experimental procedures: introducing the equipment setup, setting up data studio, exploring the interference pattern. First, introducing the equipment. Diode laser. For optical power stability, allow the laser to warm up for 5 to 10 minutes. To maximize laser life, Turn off the laser when it is unattended or not in use. Multiple and double slits. Each slit pattern is characterized by the number of slits, the slit width A, and the center-to-center spacing D, as shown in the figure below. Aperture bracket. The aperture bracket acts as a mask and holder for a light sensor. By rotating a disc, you can select various apertures to control the sensor's spatial resolution and the amount of light entering the sensor. A removable screen displays light cast to the left and right of the aperture. Slit apertures. The 6 slit apertures are typically used when scanning the sensor across a spectrum or a diffraction pattern. Select a wider slit to allow more light into the sensor or a narrower slit to improve the spatial resolution. The approximate widths of the apertures are 0.1, 0.2, 0.3, 0.51, and 1.5 millimeters. Second, experiment setup. Mount the double slit accessory to the optics bench. Align the laser beam with the slit. Mount the diode laser at one end of the bench. Adjust the position of the beam from left to right and up to down until the beam is centered on the slit. The knobs to do this are on the back of the diode laser. Prepare the rotary motion sensor and the light sensor. Plug the RMS and the light sensor into the interface. Third, setting up Data Studio. Open Data Studio and choose Create Experiment. There are 7 channels to choose from, digital and analog. Connect the sensor to channel A of the interface. In the same window under Measurement, set the rate to 20 Hz. Also, under Calibration Sensitivity, select Med 10, and later you will set the gain of the laser 10. Connect the RMS to channels 1 and 2 of the interface. On the same window, adjust the properties of the RMS as shown in the video. Drag the intensity icon from the data list and drop it on top of the vertical axis on the graph. Now drag the position icon from the data list and drop it on top of the horizontal axis of the graph. Fourth, the double slit pattern. Start by making a note in the laboratory report of the wavelength of the laser light. It is printed on the back of the diode laser. Place the laser on the side opposite the light sensor on the track. The slit disc should be a few centimeters in front of the laser. Record in the laboratory report the distance L between the slit and the sensor. Set the light sensor aperture bracket to slit 3 or 4. Choose the double slit with the slit separation 0.25 mm and slit width 0.04 mm. Turn the laser on and set the gain switch to ×10. The pattern should be visible on the aperture bracket of the light sensor. Move the light sensor to one side of the laser pattern. Turn the lab lights off. Note, you may need to change the light sensor aperture bracket slit depending on the intensity of the other light sources in the lab. Press the start button and slowly move the sensor across the pattern by rotating the large pulley of the RMS. Click the stop button when you are finished. Use the Smart tool to measure the distance between m equals 0 and m equals 1. Repeat the measurements for the second, third, and fourth order maxima. Plot Ym as an ordinate versus m as an abscissa. Find the slope of the straight line obtained in your graph and determine the wavelength of the diode light. Repeat with a double slit set of slit separation 0.5 mm and slit width 0.04 mm. What do you think the interference pattern will look like when using multiple slit 3? Verify the dependence of ym on L and lambda using the animation below.